As you know, electric fields exert forces on charged objects. In fact, we measure electric field in units of newtons per coulomb. So if we had a charge, lowercase q, that has, let's say, exactly 1 coulomb of charge, and this electric field is exactly 1 newton per coulomb in magnitude, then the force, which would be exerted in the same direction as the electric field lines, assuming this charge Q is a positive charge, would simply be 1 newton. Of course, if this were 2 coulombs of charge, but the electric field was still 1 newton per coulomb, then the force F would no longer be 1 newton, it would be 2 newtons. If the charge was 5 coulombs and the electric field was 2 newtons per coulomb, then yeah, you guessed it, the force would be 10 newtons. We don't need to give any exact numerical values here. The point is we can find the value of the electric force as long as we know the amount of charge and the strength of the electric field. F is always equal to the amount of charge that's moved through the field times the strength of the electric field. The force is a vector that points parallel to the electric field, or in the case of a negative charge, the force would point anti-parallel to the field. Okay, so now the question is, how can we calculate the amount of work done? Well, as you know, in general, work is equal to the dot product of force and displacement. So if this charge is moved on some path, maybe like this, so that it travels from some point A to some final point B, then the amount of work at each little point, or for each small displacement along the path, I should say, we divide the path up into little incremental bits we call ds. And in some points, like this one, ds is parallel to the electric field. And for some other small parts of the displacement, ds is nearly perpendicular to the electric field. Anyway, by summing up every product of the force at each location and some small incremental path, we can total up the amount of work done as the charge moves from point A to point B. It turns out the amount of work done moving the charge on the first path shown, we'll call this, we'll call this path 1, that ends up being the same as the amount of work done on this path. And yeah, you guessed that. We'll call that path 2. Because in each case, in each of those 2 cases, the charge has moved from one line of equipotential to another line of equipotential, and it's the same difference in equipotentials. So we know that electric field lines point from regions of high electric potential towards regions of low electric potential. If we call this the electric potential that passes through point A, and this is the electric potential that passes through point B, obviously the electric potential or the line of equipotential along the first path shown is the high electric potential, and VB is the low electric potential. So work done seems to be independent of the path taken. It really only depends on what's the displacement parallel to the electric field. In any case, because this example is for a uniform electric field, we're going to make some substitutions. We're going to replace F with QE. Okay, and then we can pluck the q out of the integral sign. We get work is equal to q times the integral of E dot ds. I'm going to circle that. We're going to come back to this expression, but I can continue. I guess I could have also taken the electric field out of the integral sign because this is obviously a uniform field. So we could say work is equal to q E, and then we're just left with the integral of ds, but that's nothing more than the distance parallel to the field. So we can say that in this example, work equals QED. Okay. So if I put brackets around the Q and the E, we just recognize this as work is equal to force times distance. But what if I put brackets around the E and the D? Then we see that work is equal to Q times some special value. Now, whatever that special value is, if I want to create a symbol that represents the product of E and D, I don't know, let's just create some weird symbol. There we go. What units would that symbol have to be measured in? Work has to be in joules. Charge, as we know, is in coulombs. So I suppose the units for this strange quantity must be joules per coulomb. Actually, I don't have to make up a strange symbol for that. It already exists. We refer to that as difference in electric potential. We'll call this delta V. Actually, I changed my mind. We'll explain why I have to make this distinction. This would actually be negative delta V. Well, actually, I think we can understand that pretty clearly. Look, in this example, the force and the electric field are in the same direction. So the work being done by that electric field is positive, but the charge is moving to a point of lower electric potential. So when the work done is positive, the change in potential is negative. Okay. So let's come back to statement number 3. See, what if the electric field wasn't uniform? We couldn't move on to lines 4 and 5, but we can still give a name to this quantity, the integral of E dot ds. That must be equal to the negative change in electric potential. I'm just going to call this the big idea. This is the emphasis of our unit of study 2.1 on electric potential. Okay, so just to be clear, if we have a uniform electric field, a charge Q, and it moves some displacement D, then of course we can just say the work is equal to QED. We may recognize the product of E and D as something we call negative the change in electric potential. So we could say work equals negative Q delta V in this case. And by the way, let's think of the units once again. Electric field is in newtons per coulomb. The distance, D, is in meters. So I can think of this as Newton meters per coulomb, but a Newton meter is a joule. So yeah, sure. Delta V, once again, must be joules per coulomb. When I multiply coulombs times joules per coulomb, I end up with joules as the result. All right, and again, it doesn't matter if I move the charge along that path, the same work is done by the electric field as if this charge was just moved along the straight line path. Work done by an electric field is path independent. That's worth writing down. Which implies that the force exerted by an electric field is a conservative force. So if the charge is released from rest, then the electric field does work on the charge, positive work, reducing its electric potential value, or moving it to a point of lower electric potential. If an external agent is used to return the charge to the place it came from, then negative work is done by the electric field, positive work is done by the external agent, and the electric potential increases. So we may sometimes talk about the work done by the electric field, or we might talk about the work that's being done on the charge by some external agent. Unless otherwise stated, we're always going to assume when we speak of work, we're talking about the work that's being done by the electric field. Well, what if the electric field is non-uniform, such as the electric field due to a single point charge? So if our charge lowercase q started at point A and moved to point B, the path taken could be like the one just shown. Maybe it's a straight line path from A to B, although it wouldn't matter if that path was full of loop-de-loops and squiggly, as long as it goes from, you recognize these. This path that passes through A is a line of equipotential for this identified charge capital Q, and of course you recognize another line of equipotential passing through B. So as long as the charge moves from one equipotential to another, it doesn't matter what the path taken, it just matters what's the change in potential, right? So work is equal to the charge Q that's moved through the electric field between two different values of electric potential. The work is equal to the charge Q that's moved through the electric potential So if the change in the electric potential is negative, then the work is positive, right? Again, in this example, if this charge moves from A to B, then the displacement and the electric field both point in the same direction. They both point outward. And so the work is going to be a positive value. But it's definitely moving from a high potential to a low potential, assuming our charge, capital Q, is a positive charge, right? And so the delta V must be negative. So we can write this one of two ways. We can either say, just as we did, work equals Q times negative delta V, or we can say Q times delta V is negative the work. Either way. Oh, and one more thing to note. What if our charge lowercase q moved on a path that was along the equipotential? Then we've got a displacement or a path like this. And if we break that up into incremental bits, a bunch of little DS's, there's a DS, there's another DS, there's another DS. Well, at every one of those points, or for every one of those small displacements, the electric field and the displacement are perpendicular. And so the little bit of work done, each little dW, would be equal to E dot ds dot product we can think of this as E ds cosine theta. Cosine of 90 degrees is equal to 0. And so no work would be done, But that's the whole point of an equipotential, right? It's a path along which a charge can be moved without any work being done. In other words, unless the charge gets moved to a different equipotential, no work is done, right? If there's no change in electric potential, there's no amount of work. So don't make the mistake of thinking work is equal to charge times electric potential. It's equal to charge times change in electric potential. And better yet, negative the change, because whenever the work is positive, the change is going to be negative. Okay. And to generalize it even more, if we have some very non-uniform electric field, we know the lines of equipotential have to cross the electric field lines at 90 degrees at all points where they cross. And that gets back to this idea, if the charge were moved along a path of equipotential, that means that for every little bit of displacement along that path, the electric field will always be 90 degrees to each little bit of displacement, and so no incremental work is done as the charge is moved. But if the charge moves to a different equipotential, then there must at least be some component of force that does not lie perpendicular to displacement. In other words, there must be some force that's at least has a component parallel or anti-parallel to the electric field. So if this charge were to move from A to B, it moved to a point of lower electric potential, positive work was done, and the change in electric potential was negative. If it goes from B to C, again, positive work was done by the electric field, and the electric potential went down even more. Of course, if an external agent were brought into it, so that the charge isn't released from rest, but something pushes, sort of like pushing an object upstream in a river, right? If something pushes to bring it to a point of higher electric potential, then the work done by that external agent is positive, meaning the work done by the electric field was negative. Anyway, whether the charge moves directly on the shortest path that gets it from equipotential A to B, or if it moves on some very bizarre path that gets it from A to B, doesn't make a difference what the shape of the path is. Work done by an electric field is path independent, because work is equal to Q times negative the change in electric potential, regardless of the path taken. Okay, so there's an introduction to the whole concept of electric potential difference and how we can use it to calculate work.